When you were a child, were you always annoyed by the ants constantly reaching for your leftover desserts? No matter how many times you erased their paths, they always seemed to come back. Or as an adult, aren't you a little bit curious about how ants are able to form a path from their anthills to wherever they plan on going? Did you know that these invisible paths are actually trails formed by pheromones? Pheromones are chemicals released by ants which signal other ants to follow the path. They are like the ultimate GPS for ants, helping them find food or steer clear of danger. What's fascinating about these pheromone trails is that they usually represent the shortest path from the anthill to the target destination. And what's even more intriguing is that these trails seem to persist even after erasing parts of them. In our research, we sought to simulate the formation of pheromone trails in a 2D lattice and a lattice network and examine their sensitivity to noise. We created a 2D lattice with randomly initialized origins and destination for each trial. Ants moved through this lattice guided by the quantity of pheromones in the neighboring vicinity. To enhance the model, we introduced another type of pheromone that enabled ants to sense the direction of the pheromone trail. Unlike the pheromones dropped in space, this type of pheromone was carried by the ants themselves, kind of like a built-in compass. To simulate the process of trail erasure, we implemented a probabilistic method of turning off cells in the 2D lattice, making some cells inaccessible similar to the effect of rainfall. This meant that inaccessible spaces or areas experiencing rain had their pheromones removed. Taking our model a step further, we applied it to a uniform lattice network where nodes could connect with each other as long as they are within reach. In both spaces, our goal was to evaluate the success rate of trail formation, quantify the paths formed, determine if they were the shortest paths, and assess their persistence over time.